Alright, silly people, here's the situation. We have this decent-sized wave function here that Griffiths wants us to check against the time-dependent Schrodinger equation, as well as try and get the expectation value for the Hamiltonian from it. Um, so I tried to write it, first of all, like how Griffiths wrote it, but I'm immediately going to rewrite it now using a little bit of a mathematical definition that you can write the absolute value of any function x as x times theta of x minus x theta minus x, where the theta function is just um, 1 from x greater than 0 and 0 for x less than 0. So that's kind of how you write that. Um, so writing it like that, we have this term still over h bar, and then I don't know why it's like that all the time, but like we get to keep the exponent of the imaginary stuff that doesn't involve an absolute value function. So, but now I'm going to write it like this instead of how Griffiths wrote it. Over nothing. No, it's over 2 times t minus mvx. Right? But then also times another exponent, which is going to be minus m alpha over h bar squared times a bunch of shit. So x minus vt times theta of x minus vt minus x minus vt theta vt minus x. Right? So that's cool. So the Schrodinger equation is this. It's minus I h bar. It's not even that. It's just I h bar del psi del t equals minus h bar squared over 2m del squared psi del x plus, and then the potential was actually minus alpha delta x minus vt times psi. So we're going to have to do some derivatives, obviously. So let's do the left-hand side first, which is going to be I h bar times the time derivative of this, what I just wrote up here. So we still are going to have the root m alpha over h bar times the big exponent whenever we do the derivative. So instead of writing all that, let's just write psi of x and t, and then just do the derivative of all of the arguments of the exponent. So that's going to be minus I over h bar times e plus mv squared over 2. That's the only term that gets saved there. But then also all of the time derivatives of this stuff. So minus m alpha over h bar squared. And then here we'll have minus v times the theta x minus vt plus v times theta vt minus x. And then we're going to get a couple of delta functions because the derivative of the Heaviside function is the delta function. So we're going to get plus x minus vt times delta x minus vt plus another x minus vt, but this one times the delta vt minus x. Right. And I think that should be it. Yeah, that's it. The funny thing is that this combination of delta function on x minus vt is going to go to 0 because it's either going to set x to vt, and so this is 0, or it's going to set vt to x, so it's still 0. So both of these terms we can handily cancel out. They're both 0 by themselves. And there's the end of the parentheses there. So we're going to, and even there's going to be an IH bar out in front of all of it because it's still IH bar times that. So moving the IH bar in, we actually have psi of x and t. I squared is minus 1, so this is just e plus mv squared over 2. And then it's minus I m alpha over h bar. And let's actually flip this stuff inside for funsies. So we have just v theta x minus vt. Let's move the v out as well because both of these terms depend on v. And then minus theta vt minus x. That's all we're doing. Cool. So now we need to do the right-hand side. So we need to start by doing the first derivative of the wave function. So again, you're going to end up with the normalization factor and also the exponent again. So you're going to end up with the wave function getting back out of it. But then you also have the derivative of the argument with respect to x now. So that's now going to be minus m alpha over h bar squared. You get this theta function of x minus vt, and then minus the theta function vt minus x, plus x minus vt times the delta function of x minus vt, again, which goes to 0 by itself, minus, or it's still plus, x minus vt times delta x minus vt goes to 0 by itself. And then you also get the terms which came from the imaginary term, which honestly isn't that big because it does end up just being plus imv over h bar, right? Because it's just, yeah, the only thing which depends on x in this whole term is minus mvx. So you just get, yeah, plus imv over h bar. Cool. Let's write that again, just so it's not so completely just terrible to look at. Because we're going to need to take another derivative of this, and I don't want to think about the other terms anymore. Right? Okay. Second derivative then. By the product rule, this is just del psi del x times this stuff in the brackets on the previous line plus psi of x and t times the derivative of the stuff that's in the brackets with respect to x. Right? Show. Looks like we got a psi of x and t times the junk in the brackets squared. So let's write that out. Theta x minus vt minus theta vt minus x plus imv over h bar all squared plus psi of x and t times the derivative of the stuff in the brackets, which is going to be too big to stick at the end of that line. So let's pull it down here. and be like this is minus m alpha over h bar squared, and in here you'll have delta of x minus vt plus delta x, or it's vt minus x there. But it doesn't matter because the delta function is actually symmetric, so those will just add up. Okay. Let's keep cooking with this, I think, because we need to expand that square. Oh my gosh. So it's going to be m squared alpha squared h bar to the fourth, and then this stuff with the heavy side functions squared. Whenever you square a heavy side function, you just get a heavy side function. And then the cross terms will cancel each other out because they're each 0 in the region where the other one of them is 1. So you get that. You also get minus m squared v squared over h bar squared. And then plus, no, it's minus 2im squared alpha v times h bar third times the heavy side function stuff. Yeah. This is all very annoying to write, if I'm honest, because it is just a big wave function. Minus 2m alpha over h bar squared delta x minus vt. All right. Also, this is quantity right here is 1, right? Because this one is 1 when x minus vt is positive, and this is 1 when x minus vt is negative, so it's always 1, right? So that simplifies as well, but I'm not going to write it just yet. Instead, I'm going to start writing out the full right-hand side of the Schrödinger equation. So basically, minus h bar squared over 2m times the stuff we just did, plus, or actually, minus alpha delta x minus vt times the wave function. So that's looking like psi of x and t times m squared alpha squared over h bar squared, but it's times minus h squared over 2m, so it's minus m alpha squared over 2 h bar times 1 minus, or it's plus now, just mv squared over 2 plus just im alpha v over h bar times theta x minus vt minus theta of vt minus x minus, and it's actually plus here, the sign switch to alpha delta x minus vt, and then the potential term will add a minus alpha delta x minus vt. So this term actually cancels out this term, and the form that we'll leave it in is x, or psi of x and t times, that's just the expression for energy, yeah, E plus mv squared over 2 plus im alpha v over h bar theta x minus vt minus theta vt minus x, and that's it. And then we compare it to what we got for the left-hand side of the Schrödinger equation, and which was this junk right here. Wouldn't you know it, they're identical. So it looks like Schrödinger is correct on that one. So this is a pretty good solution to the Schrödinger equation. Now we need to actually do the expectation value of the Hamiltonian, which isn't actually going to be that hard at all, because it's the integral over all space of psi star times the Hamiltonian acting on psi, but we just acted the Hamiltonian on psi, and we got this. That was the result. So we're going to have the integral over all space of psi squared times e plus mv squared over 2 plus im alpha over h bar times v theta x minus vt minus theta vt minus x times dx. And so the theta functions are odd functions, right? They are not symmetric around x equals 0. They both kind of look like that. So odd functions, which means when you multiply it by what is the Gaussian, which is or it's not really a Gaussian, because mod squared psi, very easy to write that. It's just m alpha over h bar squared e to the minus 2 m alpha x minus vt over h bar squared. And that's it. The time component doesn't show up. So it's an exponent that is linear, which is an even function. We know that whenever we integrate even functions with odd functions that they go to 0. So we just have the e plus mv squared over 2 term times the integral of mod squared psi dx. And I'm assuming that Griffiths gave us a wave function which was normalized. I realize I'm putting a lot of trust in him for that. It looks normalized, so I'm going to assume that that integral is 1, and you get this for the expectation value of h. Right? And that makes sense. It's a wave function that is, it's like the solution for the delta function potential, but it's displaced by a velocity linearly. So you're going to have the energy value that comes from the delta function potential plus a kinetic energy. And what is this thing right here? That's kinetic energy. So it's a completely sensible answer.